Okay, for this part, the purpose of a chi-square statistical analysis is to check and see if your expected results, like those are our expected results for the F2 offspring, right? So if we actually do this, okay, so we actually take a parent generation like this, make a cross, end up with an F1 generation, which is a hybrid. If we actually run the dihybrid cross in real life on corn plants, and then look at the F2 offspring, are we going to see a 9:3:3:1 ratio of offspring? Will we actually see that? And of course, we have to just expect it to be close to that, right? Because in real life, you're not going to get exactly 16 plants only and getting exactly a 9:3:3:1. If you had 16 plants, it might be like 12 and 2. It might be different, right? But is it going to be close enough? Is the deviation close enough to be good enough, like acceptable? Okay, and so we use chi-square analysis for that purpose. Okay, so in order to do chi-square, we have to identify what we're looking for, and that's what's called the null hypothesis. So the null hypothesis, I'm going to sneeze. Maybe not. Sorry, the null hypothesis is what we expect. It's our chi-square. Assuming the 9:3:3:1, assuming Mendelian genetics is holding true, that it's actually a trait that's passed on with complete dominance and recessiveness, and that has only two alleles, or two traits and only two alleles for each trait, and so on. So the null hypothesis is just everything that we've assumed up till now. The alternative hypothesis is that something else is going on. Maybe there's more than two genes involved. Maybe there's more than two alleles involved for each gene, and so on, which would make this not be true, right? So we have an alternative hypothesis would be developed if something else was going on there, if we thought the results were pretty far off. Okay. So here is a picture that I took in the classroom of an F2, remember this is F2 generation ear of corn. Each kernel has its own genotype. Okay, so this is kind of neat. We can actually just, rather than having a whole ton of ears of corn, we can just count each kernel. So what we're going to do here is look and see, maybe I'll use the same colors here. Purple and smooth, I highlighted as yellow. All right, so purple and smooth. We're going to try to see how many are purple and smooth. And I'm just going to go across in a row and count them. All right, and if it has any purple at all, like this one does, that's purple. So 1, 2, 3, Okay, so I think I have enough here to do a statistical analysis. Remember that we were expecting these to come out in a 9-3-3-1 ratio. Certainly looks like that was the case. Just the eye test looks close enough, but let's actually do the statistical analysis and we'll see what comes of it. So perform chi-square analysis and show your work calculations. Really try to walk through this. Okay, so the AP formula sheet, I put that on here somewhere, is in Schoology. If I go to the materials and AP Bio resources, syllabus and other documents, here's our equation and formula sheet. So there's chi-square. Okay, so chi-square, I'll write it on our sheet here, equals the sum of observed minus expected squared divided by expected. So chi-square, equals observed minus expected squared divided by expected, but it's the sum of that. That's that goofy symbol there. So really what we have to do, the summation means that we have to run this thing 4 times because we have 4 things that are expected. We have a 9/16 ratio of purple and smooth, so we have to run chi-square for the purple and smooth. We have a 3/16 ratio for purple and wrinkled, and so on. So we're gonna basically do this 4 times and add it up. That's what that means. So, and that symbol just means chi-square. That we're not actually squaring anything. That is chi-square. Okay, so we're gonna figure out what does chi-square equal, and then at the end of it all, when we find out what it equals, we can use the chi-square table, and we'll use the right number of degrees of freedom, and we'll use the right p-value. So we'll talk about that when we get to that. Okay, so let's go ahead and do the math then. All right, so observed for purple and smooth. So here, purple and smooth. Observed minus expected. Well, expected isn't 9. We have to figure out, this is tricky. We have to figure out how many total we counted up here. So 69 plus 22 plus 16 plus 7. So oops, let me just do that again. $114. So if we counted up 114 total, and we expect 9 out of 16ths of those to be purple and smooth, what's 9/16 of 114? So we expected 64. I'm going to round to the nearest kernel. We expected 64 of them to be purple and smooth. So that's our expected. So observed minus expected squared divided by expected. So I'm just going to write, and then we're going to add it up, remember, because it's a sum. So purple and wrinkled that would have been observed was 22 minus, we expected 3/16 to be purple and wrinkled. So 114 times 3/16. is 21.4, so that rounds down to 21. Over expected. Okay. Next, let's take a look at the yellow and smooth. That was observed was 16 minus expected. Well, expected again is 3/16, so that would be 21. Squared divided by 21, plus finally our yellow and wrinkled, so the double recessive there. So observed was 7 minus expected. What is 1/16 times 114? Seven. So I expected 7 of the kernels, which is exactly what we got. Okay, so we've written out this. Now we have to do the summation and add them up and then compare that to our table.